So, if you like systems of equations and you like inequalities, boy, do I have a treat for you today. Systems of inequalities. Are you kidding? Awesome. Okay, so you can solve systems of inequalities in more than one way. Graphing is usually the most appropriate method, and the solution is the set of all points that are solutions of each inequality in the system. What does that mean? We'll talk. So, here is a system, and remember when we first started solving, we started using a table. So let's see if we can make a table and see how good this table is. So here's a system of inequalities. G plus m is greater than or equal to 6. 5g plus 2m is less than or equal to 20. Let's make a table of values for g and m that satisfy the second equality. The values for g and m must be whole numbers. Okay, so assume that g and m must be whole numbers. That's where that came from. So look, if g is 0, we're looking at the bottom one here. If g is 0, that's the lowest whole number. That's why we're starting there. Then we get 2m is less than or equal to 20. So m has to be less than or equal to 10. So if g is 0, m has to be less than or equal to 10. So here we can start our table. If g is 0, that m has to be less than or equal to 10. These are the whole numbers that are less than or equal to 10. If m is 0, that's the lowest m could be, then 5g is less than or equal to 20, and g is less than or equal to 4. So g can go from 0 up to 4. And then we can plug in to get all these other values. If g was 1, then we would get, if we take this right here, 5, it would be 5 times 1 is 5, plus 2m is less than or equal to 20. Subtract 5 from both sides and you get 2m is less than or equal to 15. Divide both sides by 2 and you get m is less than or equal to 7.5, but we're only whole numbers, so the m values that are less than or equal to 7.5 are 0 through 7. So we can repeat that process, then we plug in a 2 for g, and we get that we can get 0 through 5 and so on. So then we need to, so we made this chart of values that work for the bottom. Now we need to highlight the pairs of values that satisfies the first one. G plus m is greater than or equal to 6. So, is 0 plus 0 greater than or equal to 6? Nah. 0 plus 1? Nah. 0 plus 5 greater than or equal to 6? Nah. 0 plus 6? Yeah, that's greater than or equal to 6. 0 plus 7? 0 plus 8, 0 plus 9, 0 plus 10, those are all greater than or equal to 6. 1 plus 4? No. But 1 plus 5? Yeah. 1 plus 6, 1 plus 7. 2 plus 5 is 7, that's greater than or equal to 6. 2 plus 4 is 6, that's greater than or equal to 6. 3 plus 2 is 5. These are all going to be too little. So we get these values. So, the highlighted pairs are the solutions of both inequalities. So we have the points 0, 6, 0, 7, 0, 8, 0, 9, 0, 10, 1, 5, 1, 6, 1, 7, 2, 4, 2, 5. Those are the points that satisfy both inequalities. Alright, see if you got it. Here's two inequalities. Make a table and whatnot for these guys. See if you can find out all the points that are solutions to this system of inequalities. Okay, so let's look at this. Let's start with the bottom one. 3x plus 7y is less than or equal to 21. And the lowest x could be is 0. So 3 times 0 plus 7y has to be less than or equal to 21. That's 0. Divide both sides by 7, and we get y has to be less than or equal to 3. So here's my x, here's my y. I'm going to make a table. When x is 0, y has to be less than or equal to 3. So 0, 1, 2, 3. When x is 1, wait, let's plug in a 0 for y and see how big x can go. So 3x plus 7 times 0 is less than or equal to 21. So 3x has to be less than or equal to 21, which means that x has to be less than or equal to 7. So 1, 2, 3, 4, 5, 6, 7. There's my table. Alrighty then. So let's plug in for these other x values. 3 times something plus 7y less than or equal to 21. And we're going to plug in a 1. So that means 3 plus 7y is less than or equal to 21. Subtract 3 from both sides. 7y is less than or equal to 18. Divide both sides by 7, and y is less than or equal to 2 and 4/7, which means it can be 0, 1, or 2. Now let's plug in a 2 for x. 3 times 2. 3 times 2 is 6. So 6 plus 7y is less than or equal to 21. Subtract 6 from both sides, and you get 21 minus 6 is 15. Divide both sides by 7, and that's 2 and 1/7, which means that it can be 0, 1, or 2. When x is 3, 3 times 3 is 9. Subtract 9 from both sides, and you get 7y is less than or equal to 12. 12 divided by 7 is 1 and 5/7. So if y is less than or equal to that, then it can be 0 or 1. When x is 4, 3 times 4 is 12. Subtract 12 from both sides. 21 minus 12 is 9. Divide both sides by 7, and y is less than or equal to 1 and 2/7, which means it could be 0 or 1. When x is 5, 3 times 5 is 15. Subtract 15 from each side. 21 minus 15 is 6. So y has to be less than or equal to 6/7, which means it can only be 0. When x is 6, 3 times 6 is 18. Subtract 18 from both sides. 21 minus 18 is 3. So y is less than or equal to 3/7, which means it can only be 0. And when x is 7, 3 times 7 is 21. Subtract 21 from both sides. You get 7y is less than or equal to 0. So y is less than or equal to 0. So it can only be 0. Now, we need to highlight the ordered pairs that satisfy this equation. X plus y is greater than 4. So, 0 plus 3, is that greater than 4? No. None of these are going to be greater than 4. 1 plus 2, no, that's not going to work. Nothing here when you add x plus y is going to be greater than 4. How about 2 plus 2? It equals 4, but it's not greater than 4. This is strictly greater than 4, so I can't get anything there. 3 plus 1? Nope. 4 plus 1 is 5. That's greater than 4. 5, 0. 5 plus 0 is greater than 4. 6 plus 0 is greater than 4. 7 plus 0 is greater than 4. So this system has 4 points that are solutions with whole number coordinates. Cool. Alright. Please tell me there's a better way than that, right? And there is, and it's called graphing. So, what's the solution to this system of inequalities? Let's graph. I got this one right here, which is y greater than or equal to negative 1/2 x plus 1. That's already in slope-intercept form. And then we can put this one in slope-intercept form. We got 2x minus y is greater than or equal to negative 3. So subtract 2x from each side, and you get negative y is greater than or equal to negative 2x minus 3. And then if you divide both sides by negative 1, you get y. Remember, when you divide by negative, this switches, so less than or equal to 2x plus 3. So let's graph y is less than or equal to 2x plus 3. So my y-intercept is 0, 3. And my slope is 2, which is 2 over 1. Up 2 over 1. And then it is a solid line because it's less than or equal to. And less than, y less than means shade below. Now let's graph the sky. My y-intercept is 0, 1. My slope is negative 1/2, so that's down 1 to the right 2. It is also a solid line because it's greater than or equal to. And then since y is greater than, we're going to shade above. And now wherever the red shading and the blue shading overlap is the solutions to the system. So this area is both greater than the line negative 1/2 x plus 1, and it's less than or equal to y equals 2x plus 3. So this purple area is where all of our solutions are. And if it was a question of only whole numbers count, then it would just be every grid point here, that's all integer values. But there are, in this case, this doesn't have to be just integers. You can have an infinite number of points. You can have 1, 2.1, 1, 2.2, 1, 2.3, 1, 2.4, 1, 2.5. There's a billion, gajillion, infinity points in this solution area. So let's see if you can graph that. BT dubs, you're probably going to need some graph paper. You can just look up graph paper, printable graph paper on the internet, and you'll find some. Okay, so let's do this. So we got, this one's already in slope-intercept form. My intercept is negative 1, so right about here. My slope is negative 1, so that's down 1, right 1. And it's greater than or equal to, so solid line. Y is greater than, so shade above. This one we need to get in slope-intercept form. We got x plus 2y is less than or equal to 4. Subtract x from both sides, and we get 2y is less than or equal to negative x plus 4. Divide both sides by 2, and you get y is less than or equal to negative 1/2 x plus 2. So my y-intercept is 2. My slope is negative 1/2, so down 1 over 2. It is a solid line because it's got the equal to sign under it. And it is y less than, so we're going to shade below this line. And now where the shadings overlap is the area where all your solutions are. So this purple area is the solutions to the system of inequalities listed up here. Cool, dude. So we can actually use systems of inequalities in real life, believe it or not. Your city's cultural center is sponsoring a concert. They want to raise at least $30,000 for the city's youth services. Tickets are $20 for balcony seats and $30 for orchestra seats. The center has 500 orchestra seats. How many of each type must they sell? So $20 times the number of balcony seats plus $30 times the number of orchestra seats. has to be more than or equal to, they want to raise at least $30,000, so greater than or equal to 30,000. And the center has 500 orchestra seats. So the orchestra seats, the number of orchestra seats has to be less than or equal to 500. So if we let x be balcony seats and y be orchestra seats, we get this system of equation. 20x plus 30y greater than or equal to 30,000, and y less than or equal to 500. Allow me to introduce you to the Desmos graphing calculator that you can find on what I like to call the internet. And I can just graph 20x plus 30y less than or equal, no, greater than or equal to 30,000. And you're like, hey, where is it? And I'm like, well, la la la, zoom out, zoom out, zoom out, zoom out, zoom out. Hey, we're starting to see it. Okay, so there's our big inequality. It's huge. Now let's graph the other one. Y is less than or equal to 500. And now look, we can't have negative orchestra seats. We can't have negative balcony seats. So we really only care about quadrant 1 here. So let's kind of zoom in a little bit on, stop doing that. Zoom in on quadrant 1 a little bit. And you can cut a little picture of that if you like or something. I happen to have already done so. And I put it right here. And so you can see that your solutions are all in this area where the red and blue graphs are overlapping and sort of making it purple. Now, in real life, there's probably going to be a limit to the balcony seats too, right? So say if they have only 800 balcony seats, then it would have to be, part of your thing would say, well, you would have to say that x is less than or equal to 800, which would give you a vertical line right here, and we would shade to this way, which would give you a really small area of values that you could do. It would have to be less than 800 balcony seats and less than 500, but then you can only be in this little area right up here. So I don't know how many balcony seats there are. They didn't tell me. But depending on how many balcony seats, you can pick a point over here and that'll satisfy your $30,000 requirement. Alright, check this out. See if you can do this problem. Alright, so we're talking about vegetable toppings and meat toppings. So let's let x be the number of veggie toppings. And let's let y equal the number of meat toppings. And so let's see, we want to get at least 5 toppings. So we want x plus y to be greater than or equal to 5. And we have $10 to spend on toppings. So something's going to have to be less than or equal to $10. And that's how much our stuff costs. So $1 for each vegetable topping, so that's 1x, plus $2 for each meat topping, so that's 2y, is what has to be less than or equal to 10. So we got this system of equations. Let's graph it. We need x plus y to be greater than or equal to 5. And we want x plus 2y to be less than or equal to 10. Alright, now let's take a look at this region here. We got this triangle here that tells us where our possible solutions are. But now look, we're talking about x and y are toppings, and you can't get like 1.5 toppings, so these all have to be integer values. So every integer point of intersection in here, like say 5, 0, 5, 0 would count, right? What about 5, 1? That would work. So that means I get 5 veggies and no meats, which is probably what I would order. 5 veggies and 1 meats, which I would not order. You could get 5 veggies and 2 meats. Could you get 5 veggies and 3 meats? No, you can't. So that doesn't work. What if you want 4 veggies? 4 veggies. 4 veggies and 4 meats? No. What about 4 veggies and 3 meats? Yeah, you could do that. What about 4 veggies and 2 meats? Yep. 4 veggies and 1 meats? Yep. Yep. So basically any point in this region that has integer x and y coordinates is a solution to that system. So you have lots of options in there. Just loads of options. And I probably should mention that your secret code phrase is pickle butter. Pickle butter. Okay, so what's the solution to this system of inequalities? Let's graph this by awesomeness. Alright, so we got y is less than or equal to 3. That is a horizontal line. The horizontal line y equals 3. And less than or equal to that, so basically everywhere where y values are less than or equal to 3. So all along this line the y values are equal to 3, and everywhere below this line the y values are less than 3. And what about this guy? We got one of these absolute value deals over here. Y is greater than or equal to the absolute value of x minus 1. Well, the absolute value of x minus 1 is just a translation of the absolute value function, which looks like this, right? Going through the origin. And a minus 1 in here is a movement to the right of 1 unit. So my new vertex will be at 1, 0. And then the slope is 1, so it's going to be a slope of 1 to the right and a slope of negative 1 to the left. And this is greater than or equal to, so we are going to shade above that. And then where the shadings intersect is where the solutions to that system are. So that's pretty cool, right? I think it is. So, what's the solution to this system of inequalities? Can you dig it? Alright, so for this one we're starting at the y-intercept of 1. We have a slope of negative 1/3, so that's down 1 over 3. And it's a dotted dashed line because it's not less than or equal to, so we don't include the boundary here. It is below, so we will shade below the dashed line. And then this is almost like the graph we had in the last problem. It's a translation 1 unit to the right, so our vertex will be 1 unit to the right, but now our slope is 2. It's going to be a vertical stretch by a factor of 2, which means that when we go over 1, instead of going up 1, we're going to go up 2. And it's greater than that, so we're going to shade above. And then you can see this teeny little spot in here where the shadings intersect. And that is the tiny little solutions to that inequality, which, believe it or not, there are still infinitely many of. Can you believe that? You should. It's math. Hey, we're done. Talk to you later. Email me. Let's keep in touch. Be nice to people. Say nice words. Bye.